Alright, section 5.2, kinetic energy. So in section 5.1 we introduced the concept of work, which was a force applied over a distance. And that was our first introduction to the concept of energy, which I'll remind you again is measured in joules. Okay, so we're going to move into something called kinetic energy, which is the energy of moving objects. And hopefully by the end of today we should be able to calculate the kinetic energy of an object. And again, we're going to be taking this energy concept, which is a massive concept, and we're just going to be adding little pieces to it as we move along. So at the end of today, tomorrow, the next day, you're not going to be an energy expert, but you are going to have a better understanding of what's happening with moving objects and with other things that have energy in them. Okay, so here's a big scary proof. Let's hide a little bit of it so you don't get too freaked out. So we are going to start with things we know. Okay, so we're going to take a couple ideas that you've seen, some of them from our force chapter, some of them from our kinematics chapter. We're going to bring them all together. We're going to make a few assumptions to try and simplify the problem, and we're going to come up eventually with a nice, easy little formula to use to solve problems. Okay, so if we start with our work equation, which is measured in Newton meters or joules, those are one and the same. And if we take our force equation, measured in newtons. Okay, so there's our work equation. We've got the cosine in there in case they're at angles. We'll simplify that out in a minute. We have our F net expression, F equals ma. Okay, and what we're going to do is we're going to bring those two together. So you can see right here that the F net gets replaced with ma. And so I have this new equation that's starting to develop. I'm then going to come over here and I'm going to grab a kinematic equation. Okay, and I'm going to isolate the A delta D, the AD part. Okay, so I'm going to isolate that. And I'm going to bring that over back to my work equation. And at first it looks like it's going to get really messy, but bear with me, it will get easier. And again, you're not responsible for this proof. It's just really interesting to see that you are more than capable of following it. Okay, so here comes our first assumption. So assumption number one, force and therefore our acceleration are in the same direction as the displacement. So that means theta, or our angle, is 0, which means cos of 0 is 1. So that takes this term right here. It doesn't set it to 0, it sets it to 1. Okay, so that's our first assumption. Okay, now I've set up a little orange box here. This little formula right here, because it's part of assumption number 2. We will come back to this near the end of today's lecture or chat, and we're going to talk a little bit more about that expression. Assumption number 2, object is starting from rest. So if the object is starting from rest, my initial velocity is 0, which means this term right here goes to 0. So we started with a very busy looking formula. We've done a little bit of work. We've made 2 assumptions, and now we have a very small little formula which we're just going to tweak a little bit more. Okay, so we're almost there. So this is what we brought from the other page. Okay, so what I'm going to do is, instead of saying the net work done, I'm going to call this my kinetic energy. Okay, and instead of putting in the final velocity, I'm just going to say it's the velocity of the object, and we're going to work under the assumption that it started from rest. Okay, so here is my new equation. So if you're doing your formula sheet, okay, this would be something you definitely want to have on there. Over here you'll see analyzing from a unit perspective. So here's mass, okay, which is the m in the expression. Here's the velocity, which is meters per second, and then I'm going to square both of those. Okay, so now if I expand that, okay, that ends up being kilograms times meters squared per second squared, which is a really confusing term when you write it like that. But if you break it up and move things around a little bit, okay, so I'm going to extract 1 meter right from here. I'm just not going to write it as a squared term. I'm just going to write it out by itself. Okay, and then what we should see is a kilogram meter per second squared. That's the definition of a Newton. Okay, so now I would have a Newton times a meter, And when we were looking at our initial energy discussion in 5.1, when we had a force applied over a distance, a Newton meter is the same as a joule. And there we are. So this balances. Okay, so this is the formula for the energy of an object. It's measured in joules or Newton meters. Okay, and it's a moving object, so it needs to have some sort of velocity. Okay, so let's calculate the kinetic energy of a 150-gram baseball that is traveling toward home plate at a constant speed of 35 meters per second. And again, because this is our intro, a lot of things will be simplified. Okay, a baseball doesn't travel at 35 meters per second the entire way to home plate. Okay, so we're just going to make some simplifications to make sure our calculations and our understanding are in place before we make things more complicated. So the first thing we want to highlight is this guy right here is not in kilograms. Okay, so that's an issue. So we're going to convert that, and you can see they've done that right here, to 0.15 kilograms. So that's something you need to spot right away. Our velocity is in meters per second, which is good. Okay, and now we have our expression. Kinetic energy equals mass times velocity squared over 2. And all we have to do is plug in the appropriate numbers and let the calculator do all the hard work. Okay, so we can do 0.15 times 35 squared, that's really important, divided by 2. Okay, so we would have 91 point, let's just say 9 joules. Okay, so please make a note. That squared term right there is probably the single most popular mistake people make with kinetic energy. It's just really easy to forget it. Please don't. Okay, so if we want to pause and try to, none of these are particularly difficult. The formula, I'll rewrite it here for you. And you can give them a whirl. It might also be written like this. Instead of having it all over 2, you can put the half out front. So pause it here and then give them a try. Okay, let's come back here. So let's take a look now. A 70 kilogram athlete. So let's do number 1. So I have a mass of 70 kilograms, so that's in the right units. It's running at 12 meters per second. What is the kinetic energy of the athlete? Okay, so if we look at EK, there's nothing in there about distance. Okay, so at this point in time, we don't need that. So we have 70 times 12 squared all over 2. And when we do that, we get 5,040 joules. Okay, so now if I erase their answer, they're going to round that off to 5 kilojoules. So remember the prefix kilo is 1,000. So they're rounding that off to 5 kilojoules. Cool. All right, number 2. Let's change to blue. 2. A dynamics cart has a kinetic energy of 4.2 joules when moving across the floor at 5 meters per second. What is the mass of the cart? Okay, so the same thing. Our nice little equation. Mass, velocity squared, 2. We have 4.2 joules, which is the correct unit, so that's good. There's no prefixes to worry about. We don't know the mass, and we know this is 5 squared all over 2. Okay, so with a little bit of rearranging, so we'll go 4.2 times 2 divided by 25. We have 0.34 kilograms would be our mass. Okay, so let's just see how much they rounded. Oh, spot on. Okay, and then lastly, a 150-gram bird. So right away, that's a concern. Let's see if I can fit this in here, if it's got enough room. Goes into a dive, reaching a kinetic energy of 30 joules. What is the speed of the bird? Okay, so the last case, of course, they're going to solve for the unknown v. So I'm going to work with this green. I'm going to put 30 in for joules. I'm going to put in a mass of 0.150. I don't know velocity, and it's all over 2. Okay, so a little rearranging. I'm going to go 30 times 2 divided by 0.15 is 400 equals v squared. Now, as just a reminder, how do you undo a squared term? You square root both sides. Okay, so I would get 20 meters per second is my velocity, and same as the textbook. Okay, so something to consider. A mass m is traveling at v meters per second. What happens to the kinetic energy when, okay, this is a very popular IB kind of question, the mass doubles in magnitude. So if we take our original expression, okay, and I'm going to space it out just a little bit. There's my original expression. If I double the mass, I can see very clearly I have the original times 2. So in this case, if I double the mass, the energy doubles. Makes sense, fairly predictable. Okay, now the next one. What happens to the system if the velocity doubles in magnitude? Okay, so we're going to start that a little bit down here. And this is where I have to be a little bit more careful. I'm going to put the 2 inside the bracket. Now that's a really important step. Okay, so when we square this bracket, okay, we end up with EK equals 4mv squared all over 2. And now you can see here, there's the original expression, mass times velocity squared over 2. So when you double the velocity, because that term is squared in the equation, the energy is quadrupled. Okay, and that's a really important thing to notice. Okay, and then lastly, the mass is tripled and the velocity is tripled. Okay, so we got lots going on in this one. So now I'm going to take that mass and I'm going to triple it. I'm going to take that velocity and I'm going to triple it. And all of that is going to go over 2. Okay, so now if we multiply out this term right here, this is going to become 9v squared. Now 9 times 3, I'm going to end up with 27 mass velocity squared over 2. So you can see there that by tripling the mass and tripling the velocity, I actually end up with 27 times more energy in this problem. Okay, so that's just keep in mind how those terms behave. Those are important things that show up, especially in multiple choice questions. Okay, so last part, the relationship between mechanical work and kinetic energy. Now, this expression right here was in our proof. Okay, it had an orange box around it, so if you want to scroll back a little bit, this is the equation, okay, before we make the assumption that the initial velocity is 0. So when we made our original kinetic energy formula, we assumed this term would go to 0. But what if the object is moving when it starts the problem? So if the object has initial velocity and it changes to another velocity, we can figure out how much work is done or how much energy is changed by using this expression. Okay, so none of the calculation is particularly overwhelming. It's just keeping track of some of those ideas. So I'm just going to slide down here to the red box. So this is called the work energy principle. The net amount of mechanical work done on an object equals the object's change in kinetic energy. Okay, so you'd have total work done, and we've seen this before, and I'm going to point out right down here that the work done can be expressed as F net times displacement. Okay, so keep in mind these are interchangeable. If you have your formula sheet, make sure you're adding these on here. Okay, and EK2 minus EK1, it doesn't always have to be positive. That's another thing to keep in mind. You could have positive energy, you could have negative energy. Okay, and we'll expand that concept as we move along. So let's try a question. So a 165-gram hockey puck initially at rest. Okay, so that right there tells me something. There's VI is 0. Okay, so that's important. Okay, I also see this guy's in grams, so I don't like that either. So I'm going to make a little note of that. Is pushed by a hockey stick on a slippery horizontal ice surface by a constant horizontal force. Okay, that was one of the other things we talked about in our course, is that for grade 11, our forces will be constant until there's a change in the problem. Okay, in which case we'll break the problem up into smaller pieces. So there's a horizontal force of 5 newtons. Okay, and we're going to assume the ice is frictionless. We'll deal with that stuff later on. Okay, what is the puck speed after it has moved 0.5 meters? Okay, so if we start with this expression right here, okay, we can fill in some pieces. So the net work done will be 1/2 mass, come on, V final squared minus 0. Okay, so this is 0 again because the initial velocity is 0, so EK1 is 0. Okay, so if we look here, we know mass, which is good. Okay, we don't know the speed, but that's what it's asking for. Okay, so this is what I am trying to find, which means I have to find something about this side. Okay, and we have to remember that work can also be expressed as force times distance or displacement. Okay, so I can take this expression and I can say force, which we know is 5 newtons. That 5 newtons was applied over 0.5 meters. I know my equation for your kinetic energy is 1/2 mass. The mass of the hockey puck is 0.165. And then my V final is all squared, and that's what I'm trying to solve for. Okay, so let's just do a quick bit of calculating here. So I'm going to say, I'm going to do this like this. 2 times 5 times 0.5. So I've brought the 2 across by multiplying both sides by 2. I'm going to divide both sides by 0.165. And then lastly, to get the V free, I'm going to square root both sides. So that should leave me with VF. Okay, so I'll just take a second to punch that in the old calculator as soon as I can get the page to move. And we should have our answer. So it would be 2 times 5 times 0.5 divided by 0.165, and then square root that. And I would have 5.5 meters per second is my final velocity. Okay, so the pieces that you want to take away from there is that this work right here can be replaced with a force times a distance. Okay, so here is your homework. If you want, I didn't include homework with today. I separated this into 2 days. So if you want to try these, you can pause it and try it. And then I'll do a quick reveal, and if there's time, I'll try and explain a few of them. So pause it here and give them a whirl. Okay, so let's just take up a little bit of them. Let's go after number 1 fairly quickly here. Okay, so a 1,300 kilogram car starts from rest. That's important. That's VI is 0, so I already know that EK1 is 0. Okay, and accelerates, interesting, okay, to a speed of 14 meters per second, so I know I have a V final here, over a displacement of 82 meters. So calculate the net work done on the car. Okay, so net work would be EK2, or EK final, whatever you want to call it, minus EK1. Okay, so net work 1/2 mass times velocity final minus 0 because it started at 0. And then I just have to put in the numbers. 1/2 1,300 V squared was 14 all squared. And then we just do that really quickly on our calculator. And we get 127,400 joules. And if we do a quick check with them, they probably rounded it off to 130,000 kilojoules. Okay, so that's just a rounding issue. Don't get panicked if you get something different. As long as you're close, we're pretty happy with that. Calculate the net force. Okay, so net force. And the other thing that jumped out at me is they gave me a distance. So if I know that this is the work done, so the net work done, I can replace with force times displacement. I know this is 127,400. They probably used 130. Don't panic, it's not a big deal. I don't know the force, and I know this is 82 meters. So if I divide that by 82, I get 1,554 newtons, and they probably rounded that off to 1,500. Just have a quick look. Or 1.6. Okay, and they're just using a scientific notation here. So this guy really is just 1,600 newtons. And I'm okay with either. I can handle the rounding. Okay, so then last part, 52 kilogram ice hockey player moving at 11 meters per second slows down and stops over a displacement of 80 meters. Okay, so let's go through. We've got a mass, which is important. Moving at 11 slows down and stops, so that means my VF is 0. Okay, so a displacement of 8 meters. So I'm already thinking forces here. Net work. Calculate the net force on the skater. My bad, sorry. So we need, let's go back and get rid of that. The net force on the skater. So sure, we can start with that. We'll start with the net work done is EK2 minus EK1, and then work net is force times displacement. My EK2 is 0 because he said he slows down and stops. That was my final velocity. My EK1 is 1/2 mass velocity I, or velocity 1 squared, and now I just have to punch in some of the numbers. So we have a displacement of 8 meters. I have a negative value I have to keep track of. That's really important. I have a 52 kilogram mass, and I have a VI of 11, which I'll have to square. Okay, so I have to do a little bit of calculating here just to come up with what this is. Make sure we can see the whole question. Okay, so we'll say 0.5 times 52 times 11 squared. Okay, so this is 8 times F, 3,146, and that would be negative. Divide both sides by 8, and I would get negative 393 newtons. And again, why is this negative? Because the force is in the opposite direction to the motion, which makes sense because this force is going to stop the object from moving at 11 meters per second down to 0. And again, the book probably has a slightly different rounding. We're not going to get too panicked on that. We had 390, or they have 390, we have 393. That's pretty close. So give 2 reasons why you can predict that the net work on the skater must be negative. I just gave you one. They had kinetic energy and they had to get down to 0, so we had to have some sort of negative energy or energy coming out of the system to slow the person down. Cool? All right, thanks for listening. That's all for today, and we'll pick this up tomorrow in section 5.2 continued.